Okay, we're back and we're ready for more example problem time. And this is going to go A through O. I told you it was A through O, but I told you that we're not going to spend forever on this. All right. So I'm not going to draw these out. I'm not going to give you full-blown explanations because I think that we have enough at this point to look at the basics and determine if the basics are going to be there. How can we quickly identify the number of NMR signals that we have? And then I will stop at ones that I think are the trickiest ones for you at this time. And then we'll talk about those. We'll flesh them out a little bit more, and I'll give you some reasoning about why the answer is what it is. All right. So here's our example problem A, and it looks like we have CH3, CH2, CH2, CH3, butane. So we've got butane that we need to put in NMR, and I think that you would recognize this and see a symmetrical line right here in the middle, right? So that means ding, 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 we're going to get a signal from the CH2, but that's also the same signal from that CH2 to the right-hand side. There's no difference here. And then ding, 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 we see a second signal that will come from a CH3 on the left, and it's the same as if it came from the CH3 to the right. So these are symmetrical hydrogens that we see, and this signal will be representative of these three as well as those three. And this second signal would be representative of those two hydrogens as well as those two hydrogens. So that takes into account all four of those. So the answer to A is going to be 2. I see 2 signals because the other CH2 and the other CH3 is a symmetrical unit. They are equivalent to each other. All right, now we take a look at B. And for B, it looks like I've got a bromine to the left and a bromine to the right. So this bromine to the left, we're going to start there first. That carbon has a CH2 group on it. And that CH2 group, because it's hydrogens already, ding, ding, we see a signal that will be presented to the NMR. Now, to the next carbon in line, I need to take a look. Is this an equivalent hydrogen or not? Well, the answer is, hopefully quickly, you can say yes. So if you look at this symmetric or line of symmetry, you're going to see that the molecule can actually fold in half here and be stacked on top of each other. So that means that the CH2 group here to the right is the same as the CH2 group to the left. Think about those meso compounds back in the day when we talked about stereochemistry and that type of thing. Diastereomers and enantiomers and so forth. So this line of symmetry and meso compounds should have been presented, and that's basically what we're dealing with here. So even if I forgot that, right? This bromine is attached to a carbon with 2 hydrogens, which is on a carbon with 2 hydrogens, right? And then over here to the right-hand side, that bromine's attached to carbon with 2 hydrogens, and that's attached to another carbon with 2 hydrogens. So it's the same story, whether you go left or whether you go right. So what this means is that we get one signal only from that compound, and that is it. All right, now let's take a look at C. C, we see 2 chlorines there. That's not going to give us hydrogen NMR. We see the carbon here that has no hydrogens to give us hydrogen NMR. And then we see another carbon that has 2 hydrogens. All right, ding, ding. I see that. There's hydrogens present. I'm going to get a signal. Now, the answer here for C is, would it be different, yes or no, depending on what we have? Well, we see a double bond, and I told you, you need to worry about those double bonds, right? So carbon, double bond, carbon. And then it looks like on this example problem, we have 2 hydrogens on the left and 2 chlorines on the right. So I'm going to draw this way because I know that cis and trans could actually be a problem here if we're not careful. So if I did do the bloop, 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 and then change that with another group like bromine, would I get a different name depending on what we have? And the answer is no. And that's because when I erase this hydrogen to the left, these would be different. However, the carbon to the right-hand side has 2 chlorines attached. So automatically, no matter if I substitute a hydrogen here or not and name it, this is still not going to give me cis and trans. And that's because 2 chlorines are over on the other carbon. So it violates those rules. And because of that, this only really does have one signal, and that is it. Now let's take a look at D. For D, it looks like I've got a signal ding ding here because that's a CH3 group on an oxygen. And then it looks like this is also going to be a ding ding, and that's because those hydrogens are not attached to an oxygen. They're directly attached to the benzene ring, right? So I'm going to automatically see 2 that's here. And then keep in mind, these are benzene rings, and it's not drawn, but they're understood to have hydrogens that are located here. So do I, in fact, get different signals from those positions? And the answer is, of course, yes, I do. Because in the benzene world, we have a substituted benzene, and then all of a sudden, I'm looking at ortho, meta, and para positions. And those positions are different, which means they are different equivalent protons, or they're not equivalent at all. They're different protons, and they're going to give me different signals in NMR. So for D, I'm going to ding ding here, and then I'm going to ding ding there for the ortho positions, and then I'm going to ding ding here for the meta positions, and then I'm going to ding ding there, which would be the para position to the original OCH3 group. The hydrogens here down at the bottom, folks, there's no difference here in the top or the bottom. So this is the top ortho, and that is the bottom ortho. They are equivalent. And then the top meta and the bottom meta. So therefore, those are equivalent as well. So what that means is that I'm going to have a total of 4 signals from that molecule in NMR. All right? Now let's take a look at E. We once again have a double bond. That's the problem. It seems like that's what these example problems are focused on because they know it's a problem and they know their common tricks where they can try to fail you in the class. Don't let them fail you. So for E, well, in the beginning, it looks like ding ding. I see a carbon that's attached to a hydrogen with a chlorine on it. And then here I see a carbon attached to a hydrogen with a chlorine on it. So at first glance, it looks like these 2 hydrogens are equivalent, right? And I might say 1 signal, that's all there is to see here. 1 signal, go on to the next example for F. Nothing to see here. Move on, please. But I just want to take the time and I want to double check it, right? That's what this thing is all about. So if I do a boop, 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 all right, so here I'm going to redraw the structure, carbon, double bond carbon, and then we get these 4 prongs. And if I go back to the original structure, there's chlorines at the top and hydrogens at the bottom. All right, so chlorines here, hydrogens there, chlorine here, hydrogen there. I want to know, are they going to be different? So when I the hydrogen and when I replace it with a bromine, do I get a different name? And here, the answer, if I look at this, there's different groups to the left on that carbon, and there's different groups on the right that's attached to that carbon. So, ding ding, yes, I do have cis and trans that can actually form. But in this particular case, it's not really cis and trans, it's going to be E and Z. Because I'm not comparing 2 hydrogens. I'm comparing 2 higher priority groups. The high priority groups were always about atomic number, right? So this is the high priority group here, and on this side, this is the high priority group. So if I compare the chlorine to the bromine, bromine trumps it out. And if I compare the chlorine to the hydrogen, chlorine trumps it out. So this is the high priority on the left. That's the high priority on the right. This is the rules of alkenes back in the day in Orgo 1. Now it's coming back to haunt you all over. Just like I said before in a previous video, everything comes back. Did you ever read that Stephen King's novel? Sometimes they come back. Well, everything comes back here in organic. Not sometimes, every time. So this position will cause this to be a trans orientation. Now, if I go back and I replace that hydrogen here, and I target the other hydrogen, I get rid of that one, and I put the bromine group on that spot, because that's the only thing that I can do to, right? Just the hydrogens, that's it. So if I go back and try this one, I once again see bromine and chlorine on the same side of the molecule, and I see bromine down here at the bottom. That's my high priority group. This one's not high priority anymore. Bromine trumps it out. And then on the other side, just need to be careful. Chlorine and hydrogen, that's what originally was there. This is high priority. And if I had to name this, folks, this is still a trans based on that ranking. So we're not getting an option to be cis here. It's still a trans. That is it. And then if I look at the nomenclature, on the first example that we did, chlorine on top, bromine on the bottom. And then this one, chlorine on top, bromine on the bottom. It's the same structure. I'm not going to get a different name just because of the way that things are ordered on this structure. So the answer to E is yes, in fact, we do have one signal because it is the same. They are, in fact, equivalent, and I just proved it. No matter which one you get rid of and replace it with a group, you're going to end up with a trans molecule that carries the same name if you named it. And because of that, they are equivalent. All right, now let's take a look at F. Look at these signals. How many? All right, well, I'm going to start here to the left. Ding, ding. I get a signal there. It's 3 hydrogens on a carbon. And then I move in and I go ding, ding. There's 2 hydrogens on a carbon here. So therefore, they're different than the 3 on that carbon. And then I move in and I question, are these 2 hydrogens different than those? And the answer is ding, ding. Yes, they are. And the reason in my head, what I'm doing is I'm comparing it to this carbonyl group, right? This is a carbonyl group, and I would name it accordingly. And if I had a bromine that was here, I would name it a certain way. And then if the bromine was here, I would name it a different way. And then if the bromine was there, I would name it a different way. So all 3 of these carbons, this one is the closest to the carbonyl, this one's a little further away, and that one's a little further away. So by definition, they are not equivalent. And I will get a different signal every time. And then finally, over here to the right-hand side, I see a CH3 group on the carbonyl. There is no other CH3 group on a carbonyl. There's a CH2 group on a carbonyl, but not a CH3 group on a carbonyl. So ding, ding, I see another signal, and that will give me a total of 4. G. How many different signals do we have? So it looks like I've got a chlorine here in the middle. That's where my eyes go to. And that chlorine has a carbon that has 1 hydrogen on it. So ding, ding, I'm going to get a signal straight up from that one. Okay. No other carbon in the lineup has just 1 hydrogen. So I know that's going to be a different signal. Then I go to, let's say, the left, right? This is a carbon with 2 hydrogens. That automatically is different than that carbon with 1 hydrogen. So ding, ding, I'm going to get a signal there. So there's my second. But if I went right-handed, that's also a CH2 group. And there's no other functional groups on the molecule. It's a very symmetrical looking molecule. So if the CH2 group on the left or the CH2 group on the right is picked, and I substitute one of those hydrogens with a bromine just to see if it's a different name, I'm not going to get a different name. So therefore, those hydrogens are equivalent. And then finally, the CH3 group on the left, ding, ding, because that has 3 hydrogens, not 2 and not 1. And then the CH3 group on the right-hand side is equivalent to that one on the left-hand side. So for G, I'm going to end up getting 3 signals in total. And that's because this carbon is equivalent to that one. It's the same distance away from that chloro group. No other functional groups that I need to look at. And then the CH3 groups on the ends are also equivalent to each other because they are 2 carbons away from that chloro group. Both of them are the same way, same story, and no other functional groups for me to look at. All right, so 3 in total. H. Let's take a look at H here. It looks very symmetrical as well, right? So if I look at H, I see the CH3 group on the left. So automatically I'm going to ding, ding. There we go. That CH3 group is on a carbon with one hydrogen. So ding, ding. I'm going to see a signal from that one as well. However, look at the CH3 group at the bottom. This is actually the same as that CH3 group that we did first. There's no difference in these. It's a CH3 group on a carbon, whether it's in the main line or whether it's hanging down, it doesn't matter. So what this means is the hydrogens that are here are actually the same as the hydrogens that are there. So this is not going to give me a different signal. These three hydrogens are equivalent to those three hydrogens. So I still have two signals. That's it. Then I move on inward. This is a CH2 group. I don't have anything with a CH2 group yet. So ding, ding. I'm going to get a signal from there. So that brings my total to 3. And then I'll move on to the next one, and this is a carbon with one hydrogen. Folks, I already taken care of carbon with one hydrogen. That carbon with one hydrogen is connected to a CH2 group. This one is too. That carbon with a hydrogen was connected to 2 methyl groups. This carbon with a hydrogen is also connected to 2 methyl groups. It's a symmetrical molecule. I do not get a signal there. It's already taken care of. It's just going to be a taller signal. And then finally, this CH3 group on the very end on the right-hand side. This is the same CH3 group as what was here in the beginning. There's no difference. And this CH3 group that's hanging down below is no different than that one that's hanging down below. These are all equivalent hydrogens. So I'm going to get a total of 3 signals here from this molecule. The first signal is going to take care of those 3 hydrogens, as well as those 3, as well as those 3, as well as these 3. They're all the same. Don't believe me? Erase the hydrogen, put a bromine on it, and name all possibilities. It's going to take a little bit of time, but you will see that you will end up with the same name no matter what you do. The next one, the signal will include this hydrogen as well as that hydrogen. They're equivalent. And then finally, the third one is going to include the 2 in the middle. That's where our 3 signals will come from. All right. Next up is I. How many NMR signals do we have? All right. So, ding, ding. We get one there. Ding, ding. We get one there because they're clearly different from each other. And this is a benzene ring. So this proton is different than that proton, which is different than that proton, because that would be ortho to that group, and that would be meta to that group, and that would be para to that group. So I'm going to quickly go ding, 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 all the way through, and that gives me a total of 5 signals. Next is J. How many do we have in J? All right. Well, this carbon, 1, 2, 3, and it's got a 4th to a hydrogen. So I'm going to draw that for you. This particular carbon, same deal. 1, 2, 3, and 4 goes here. And this particular one, same deal. 1, 2, 3, and there's 4 there. And this particular carbon, 1, 2, 3, and the 4th is there. And this particular carbon, I'm going to get a hydrogen here, and I'm going to get a hydrogen there. And in this particular carbon, I'm going to get a hydrogen here, and I'm going to get a hydrogen there. All right, so I've drawn all the hydrogens that we're missing, just to make this a little bit easier. And the question is, how many signals do we get? All right, so let's start breaking this down piece by piece. The reason it's not a benzene, it's double bonds here. These double bonds are kind of tricky. Well, first off, let's take a look at this particular carbon. This particular carbon has 2 hydrogens. So I'm definitely, ding, ding, going to get a signal from that one. And that is next door to a carbon with a double bond. This one also has 2 hydrogens. And that one also is next door to a carbon with a double bond. So these two hydrogens look like they would be equivalent to those two hydrogens. And it looks like they would give me the same signal. So I've taken care of those two. This particular carbon has one hydrogen hanging off, just like this one has one hydrogen hanging off. So it looks like that would be a signal that is definitely different than what I've already drawn. And they're equivalent to each other, so I'll circle them both in purple. And then next one in is a carbon that has a hydrogen, just like the one prior. And another carbon that has a hydrogen, just like the one prior. So the question is, are these hydrogens the same as the purple ones that I've boxed in? Well, if I look at this carbon, to the left is a carbon that is single bonded. To the right is a carbon with a double bond. Now compare that to these hydrogens. These hydrogens are attached to a carbon, and on the left is a carbon with a double, and on the right is a carbon with a double. So they are not equivalent here. So what that means is that ding, 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 I get a third signal that is coming from that compound. And folks, that means that the answer to J here is going to be 3. I get 3 different signals. The first signal comes from the carbons that have 2 hydrogens apiece. The second one is coming from a carbon that on one side has a double bond and on the other side has a single. And then the next ones are coming from a carbon that has a neighbor of a carbon with a double, and the other neighbor is a carbon with a double. Therefore, they are different. So 3 signals in total. Okay. How many different signals do we have? Okay. So I want to quickly do this. It looks like, hey, CH2, ding, ding. I get a signal from there, and then I get a signal from here because that's clearly different. And then I get a signal from here because that's clearly different. And you're going to walk away and you're going to say, hey, that's going to be 3 signals. And I'm going to say, hey, you got the wrong answer. And the reason is because of the double bond. If I take a look at that structure, and we, a hydrogen, carbon, double bond carbon. And then on the left, I have 2 hydrogens. And then on the right-hand side, I have a hydrogen. And the other spot is going to be a C double bond OH. There we go. If I erase a hydrogen and put a bromine there, this is high priority. That is high priority. I see the 2 hydrogens that I'm comparing on the same side. This is a cis version. However, if I go back to the original, and the other one, and I put my bromine there, this is high priority. That is still high priority. The hydrogens are on opposite sides. Therefore, this is a trans. That means that those 2 hydrogens are not equivalent. So, that very first carbon, tricky, because I get a second signal that comes from that other hydrogen that is not equivalent at that spot. So what this means is that the answer for K, how many signals do we have? The answer is a total of 4. All right, L, I see a benzene ring with 2 bromines already. So what they're not doing is they're not showing me a hydrogen is here and a hydrogen is there, and a hydrogen is here, and a hydrogen is there, right? They're leaving those off because it's understood that they're supposed to be there. All right, so for L, if I boop, 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 that hydrogen and put a bromine there, that is definitely going to give me a signal, right? I mean, there's a hydrogen there. It's going to be a signal. So I'm going to go ahead and ding, ding. There's one signal there. And that's in between the two bromines. Okay. Well, this hydrogen's not in between two bromines. That hydrogen is in between a carbon with a hydrogen and a carbon with a bromine. This one's different. So, ding, ding, I'm going to automatically get a signal here. And then if I take a look at this carbon up on the top left, well, that's even different because that hydrogen's on a carbon that is 1, 2 away from a bromine there and 1, 2 away from a bromine here. Ding, ding, that's going to be different. If I take a look at the top right-hand hydrogen, we've already kind of taken care of this. Look at this one to the left that we did. So what that means is that this hydrogen and this hydrogen are equivalent to each other. This one has a carbon and a bromine next door, as well as a carbon and hydrogen next door. This one, same story. I see a carbon bromine next door and a carbon hydrogen next door. There is no difference. They are equivalent at that spot. So I'm going to get a signal in between the two bromines. Then I'm going to get a second signal 1 spot away from the bromines. And then I'm going to get a third signal that's 2 spots away from the bromines, which gives me a total of 3 signals. M. Kind of already done this one already. Hydrogen, 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 hydrogen. So, ding, 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 ding. I've got 3. OMP. And the one up here at the top, didn't even look at it because it's equivalent to the one at the bottom. They are both orthos. The same for the next one. They're both metas. And we have 1 para group. So the answer to M is 3. N, let's look at this one. 2 of the same groups on the benzene ring. Well, I've got a hydrogen here, and I've got a hydrogen there, and I have a hydrogen here, and I have a hydrogen there. All right, so if I one of the hydrogens and replaced it with a bromine, well, this is ortho, so ding, ding, I get a signal. And then this one is going to be para to that one, or meta to that one. So ding, ding, I'm going to see another one. But it would be the same as if I did it up on top. I would see a ortho, and then I would see a meta if I put a bromine in those spots. So this will be a total of 2 signals. Finally, O. We've done this one somewhat as well. This will be a total of 3 signals. I get one from that hydrogen because it's on a carbon with a methyl group and a double bond. This hydrogen's different because that's on a carbon that's not on a methyl group. It has a chloro group instead. So that is not the same as the one to the right-hand side. And then this is a double bond. So I have to make sure that I don't involve cis and trans. And I do have cis and trans that show up here if I'm not careful. So that cis and trans will add on a extra choice or an extra signal for me when it concerns the NMR. So a total of 3. All right. So there's your massive example problem amount for determining the number of signals on these structures. So this will be kind of half the battle. If you can't do these examples, if you don't feel good about these, you can't go the next step and do what else we're going to do with the structures. It's not just all about determining the number of signals. We're actually going to have to go a little bit deeper than this. And that's the world of NMR that people hate. So just when you think the going's getting good, I'm going to throw a curveball and kind of make you falter a little bit and pick up the crumbs and then start all over again. I know that sounds horrible, but those things are good for you, right? So again, hope you feel good about them. And in the next video, you see where this is going to be headed.